Hi, Charles.
Hey, Michael. How's it going?
Good. Do you want to learn about temporal difference learning today?
You know what I'd like to do? I'd like to learn about temporal difference learning today.
Perfect, because that is the plan. And in fact, I need you to actually take a little bit of a break and read Sutton.
What, you mean the entire thing?
Yeah, it's just a paper. There's the Bardo and Sutton book, and Sutton and Bardo book, but this is actually the paper where he introduces temporal difference learning.
Okay, so you want me to go read that now?
Yeah, I can wait. You can just pause me.
How about if I pretend I read it, and then you take me on an odyssey of discovery?
Perfect. All right, to introduce you to temporal difference learning, it helps to have a little bit of context about reinforcement learning in a more general way so we can see how the different methods for doing reinforcement learning fit together.
Okay.
So I'm going to think about reinforcement learning this way. Remember we talked about SARS's, right? The state action reward sequence. So I'm in a state, I take an action, I get a reward back, I end up in a new state, I take a new action, I get a new reward, and this just continues. So I put a little cleany star after it to indicate that this is some sequence of state action rewards. That's what comes as input to a reinforcement learning algorithm. And what the reinforcement learning algorithm produces as output is a policy.
Sure, that makes sense. Hey, I got a quick notational question for you, though.
Sure.
Should that really be a cleany star, or should it be a plus?
Well, I'm being a little bit lax with notation here, but I'm imagining that even if you give a reinforcement learning algorithm no history at all, it could still come out with an initial policy.
Sure, that makes sense. In fact, I guess that's true for every algorithm we've ever talked about.
I think so. I mean, it could just be a default policy, like in all states take whatever the first action is. But the fact of the matter is, over time, I mean, the interesting case is when we've had some amount of history and we're trying to map that to some behavior.
Okay, I'm on the same page.
So the way I like to think about it is there's kind of three main families of reinforcement learning algorithms. So the one that's most like what we've talked about so far is what we could call model-based reinforcement learning algorithm. So model-based reinforcement learning algorithm takes the state action reward tuples that it gets and sends them to a model learner, which learns the transitions and rewards. Those transition and rewards, once you've learned them, you could put through an MDP solver, like we've talked about, which could be used to spit out a Q star, an optimal value function. And once you have the optimal value function, you can use, just by taking the argmax of the state that you're in, you can choose which action you should take in any given state, and that gives you the policy. So it's still mapping the state action reward sequence to policies, but it's doing it by creating all these sort of intermediate values in between. Cool, and let me just add one more thing, which is that the model learner takes the history that it's seeing, but it also takes its current estimate of the transitions and rewards to produce the new estimate of the transition rewards. So this is how I want to kind of represent the learning piece of the sequence. Does that make sense? All right, so this is one type. Now let me show you another type. So the second kind of class of reinforcement learning algorithm that's important to think about, they're referred to as value function based, or actually sometimes model free. So the beginning and the end of it are still the same. We're taking sequences of state action rewards and producing a policy. And we even have this Q star in between that we generate the policy from using the argmax. But now, instead of feeding back the transitions and rewards, we're actually feeding back Q star. And we have a direct value update equation that takes the state action reward that it just experienced, the current estimate of Q star. Actually, it's kind of more Q'd than Q star. And uses that to update and generate a new Q, which is then used to generate a policy. Yeah, so instead of explicitly building a model and using it, it just somehow directly learns the Q values from state actions and rewards. And then a third class of reinforcement learning algorithms comes from the idea that you could sometimes actually take the policy itself and feed that back to a policy update that directly modifies the policy based on the state action rewards that you receive. So in some sense, this is much, much more direct, but the learning problem is very difficult because the kind of feedback that you're getting about the policy isn't really very useful for directly modifying the policy. So here's these three models all together so you can compare and contrast. And you can see in some sense, they're getting kind of simpler as we go down to policy search, but you could also sort of say that the learning is more direct. And as we go up this way, the learning problems become more supervised in the sense that you can imagine learning to predict next states and next rewards from previous states and previous rewards to learn T and R pretty directly. It's basically a supervised learning problem. You get to see what the output's supposed to be. Here, you don't quite get to see what the output's supposed to be, but you do get values that you could imagine kind of propagating backwards. And here you get very little useful feedback in terms of how to change your policy to make it better.
Wait, so The way you put that suggests that you should always do 1.
Well, so yeah, but look at all the extra stuff that you're doing in between. So in fact, different problems have different trade-offs as to whether or not which of these is sort of the best thing to do. A lot of the research has been focused on number 2, and that's what we're going to be diving into, because in some ways it strikes a nice balance between keeping the computations relatively simple and keeping the learning updates relatively simple. But there are plenty of cases where you'd rather do 1 and where you'd rather do 3.
I look forward to you convincing me that that's true.
All right, and so that brings us to temporal difference learning. So temporal difference learning, the algorithm that we're going to look at, originally by Sutton, is called TD lambda. This is a little lambda symbol. So TD stands for temporal difference. And what really it's about is learning to make predictions that take place over time. And so as a concrete example, a concrete way of looking at this, we're going to look at how we can, from a sequence of states, state 0 goes to state 1, goes to state 2, goes to, let's say, a final state. And each time there's a transition, there's some reward that's associated with that. We're going to try to predict the expected sum of discounted rewards from that.
Okay. Which is what we're trying to do anyway.
Yeah, so this is going to be a really important subroutine for trying to do reinforcement learning, because we're going to use the notion that we can predict future rewards to try to better choose actions to generate high rewards.
Okay, that's fair.
All right, so for the kind of prediction problems that we're going to be learning with temporal difference methods, it's helpful to have a concrete example to kind of ground out some of these terms. So here, let's take this as a Markov chain with states S1, S2, S3, S4, S5, and SF for the final state.
Okay.
I've labeled each of the transitions with the reward that happens when you make a transition from that to the next. And this particular transition out of S3 actually is a stochastic transition with 90% probability going to S4 and 10% probability going to S5.
Okay, that makes sense.
And what we'd like to learn here is a value function, a function that maps the state to some number, where that number is set to 0 for the final state. And for every other state, it's the expected value of the reward plus the discounted value of the state that we end up in, averaged across all the different states we might end up in.
Okay, that makes sense.
Great. Okay, good. Then let's have a quiz.
Ah!
All right, and here's the quiz. What we're going to do is, since you understand this so well, figure out what VS3 should be. So what is the value of state 3 given this Markov chain? And just to make things, a little bit nicer, more friendly, just assume that gamma is 1 so you don't have to multiply by funny numbers.
Oh, that is very nice of you, Michael. All right, go.
All right, Charles, let's work this out.
Oh, we're going to work this out?
Well, you're going to work this out.
Okay, well, so I'm looking at this. I actually think this one's pretty straightforward to do once you have the first insight. And the first insight is you want to go backwards. And the reason you want to go backwards is because I already know what the answer for the final state is, and I can go back one step and use that to figure out what the states before are, and so on and so forth. So with that, why don't we actually be explicit about it then? So
yes,
the value of S sub f would be 0. That's
good.
Given. That's pretty easy. Okay. So then I can ask, well, what would be the value of S4, say? So S4 is the reward you get for leaving that state, taking the action, plus gamma times the state you're going to end up in. Well, so that would be 1 plus gamma times 0, which is 1. Oh, that's pretty good. Okay, and then for S5, I can do the same thing. In this case, it would be 10 plus gamma times 0, which, of course, is 10. All right, am I right so far?
You are right so far, but that's not the question that was asked. It was S3.
Oh, okay, fair enough. All right, so let's do S3 then. So S3 would be the reward that I get, which is be 0, plus gamma times the value of the state that I end up in. Well, if I end up in state 4, that would be 1. But sometimes I'll end up in state 5, and that would be 10. So 90% of the time I end up in 1, 10% of the time I end up in 10. So I multiply the first one by 0.9 and the second one by 0.1, and then I add them up, and we go from there. And that number is 0.9 plus 1. Is that right? Which is 1.9. And that was easy because gamma was 1.
Nice. Very good.
So I think actually you might as well go ahead and talk about what S1 and S2 would be then, because why not?
Okay.
All right, so let's see. The value of S1 would be 1 plus gamma times the value of S3, which is 1.9. And so that would be 2.9. And S2 would be 2 plus 1.9, which is 3.9. So this is good. So if there was some state 0, and I had a choice between going to state 1 and state 2 from it, I should go to state 2.
Yes, because it's just the same, except you get that extra 1 bonus going out of state 2.
Right. Okay. Yeah, that makes sense.
Great. Nicely done.
Thank you.
So let's think about how we could get those same values from data instead of knowing in advance what the model of this particular Markov chain is. So let's imagine that, in fact, what happens is we're going to do a series of simulations starting from S1. It's going to hop around, and with some probability, it's going to hop. Well, it's going to go S1 to S3, and then either S4 or S5, and then to SF, and then it stops. And so let's imagine that we've done that, and these are the episodes. These are the sequences that come out of that. So the first time we run it, it goes from S1 to S3 to S4 to SF. The next time it goes S1 to S3 to S5 to SF. Then it goes S1 to S3 to S4 to SF, and so on. So what I'm interested in is how we would actually develop an estimate of the value of state 1 given just this data after, say, the first 3 episodes or the first 4 episodes. The 5th episode doesn't involve S1, so presumably it shouldn't. Well, we'll get to what happens then. But first I want to think about after the first 3 or after the first 4. Does that make sense?
Sure. I can do that.
Excellent. All right, so do that.
All right, go.
All right, so do you have an answer for this quiz?
I don't, but I think I know how to get one.
Let's go for it.
Okay, so basically you're asking me to estimate from data. So what you're really doing is you're asking me to do an expectation, right?
Right, because that's what we're trying to estimate is an expectation.
Right, and the way you do that is you just average things. So
Yeah,
I should just be able to do that. So I can look at episode 1 and I can see what the value for S1 turned out to be. And because you were so nice and made gamma equal to 1, I can basically just add up the numbers on the arrows, right?
Yep.
So the value to S1 in episode 1 is 2.
Good.
And the value to S1 in episode 2 is 11.
Good.
And the value to S1 in episode 3 is 2 again.
Good.
All right. So then if I wanted to know what an appropriate estimate was after 3 episodes, I would just average those 3 numbers, and I would get 5. Is that right?
Yeah, so 15 over 3, which is 5.
Nice.
Good.
Okay. So then for 4, I see 2 again, and so that would be 17 over 4.
Good.
Which is a number. 4.25.
Good. Yeah, that's what I was looking for. Nicely done.
Oh, so in fact, I could do this for 1 episode or 2 episodes.
That's right. In fact, what we're going to work up to next is how we can incrementally compute an estimate for the value of a state given the previous estimate, right? Given after 3 episodes, how do we get 4? And 4, how do we get 5? And 5, how do we get 6? And then in, 10,000, how do we get 10,001?
Okay, well, can I ask you a question?
Sure.
So I'm curious how close we came because, you go from episode 3 to episode 4, you went from 5 to 4.25. That's kind of a big jump. So do you remember from the last quiz what the value of S1 was? I think it was 2 point something.
2.9, that's right.
Oh, it was 2.9.
Yeah, so in principle, with an infinite amount of data, that's what we should get. We should get 2.9 as our estimate for S1. In this particular case, we're actually a little bit high. Why do you suppose we're a little bit high?
Because we just haven't seen enough data yet. We saw 11 once. And so it looks like for 3 episodes, 11 happens a third of the time instead of a tenth of the time.
That's right. Yeah, so we have kind of an overrepresentation of the high reward. So our estimate ends up being skewed high.
Okay, that makes sense.
In the limit, it should all start to work out, and we'll get 1/10 plus 11s. But in this case, we got, I don't know, let's call it lucky. We got a higher reward than the expectation would predict.
Okay.
Okay, Charles, I'm going to see if I can get you to derive a piece of the temporal difference equation just by working through this example again in a slightly different way. So from the last thing we talked about, we said that the value estimate for S1 after 3 episodes was 5.
Mm-hmm.
And then we ran an episode, and the return of that episode, the total discounted reward for that episode number 4, starting from that state S1, was +2.
Mm-hmm.
Could we, just from this information, figure out what the new estimate's going to be?
Sure.
So let's see if we can do that. Let's work through that step by step.
Oh, okay. Well, I can cheat, right? By just, I mean, you have everything indexed by time, so I know that 5 is an estimate of the last 3, and 4 is an estimate of the fourth one.
Right?
So I should be able to, weight the first one with 3 and the other one with 1 or something like that, and that'll give me the right answer.
All right. So what do you mean by weight? So what you mean is since 5 is the average of the first 3 episodes,
It's
then
as if I saw
15
5.
is the total from the first 3 episodes, right?
That's right. I've seen it 3 times.
Good. It's as if we had seen 5 3 times. Though the details actually varied from that, but that's okay because averages work out nicely.
That's right. Doesn't matter.
Then we got an additional reward of 2,
Mm-hmm.
and now we want to know the average over 4 steps, right?
Mm-hmm.
So that gives us 15 plus 2 divided by 4 is 17 over 4, which is just the answer that we had in the quiz.
In fact, that's exactly how I did it. I just took the 15 over 3 that you had written down and just said, oh, so that'll be 17 over 4.
Good. So now let's generalize this a little bit and put in some letters because, math. So
Okay.
let's say instead that we're talking about the previous estimate, which was from time t minus 1. Then we get a return on step t of t, and now we want to compute the new estimate vt of S1. So we should be able to do that same kind of calculation with these quantities, just symbolically. Okay, so you want to try that again?
Sure. So I think I know what Vt of S1 is equal to t minus 1 times V sub t minus 1 of S1 plus R sub t of S1 divided by t.
Good, which was 4 before, but now in general it's t.
Mhm.
Excellent. All right, so let's now do a little bit of algebra on this.
Oh, sure.
So first I'm just going to divide through by this capital T and split it into 2 pieces of the sum.
Okay.
All right, and so then we can regroup things as follows. Let's see. So I guess mainly the idea is that we split this t minus 1 over t into a t over t and a minus 1 over t. So that gets us vt minus 1 of S1 plus 1 over t of RT S1 minus VT minus 1 S1. So I wrote it kind of funky. I introduced this additional learning rate parameter alpha sub t, the learning rate at time step t, but it's really just playing the role of 1 over t here, the averaging. But there's an interesting thing that popped out of this particular way of rewriting it, in that we are looking at a kind of a temporal difference, that our update to the value is going to equal the difference between the reward that we got at this step and the estimate that we had at the previous step. And so this difference is actually going to drive the learning. So if the difference is 0, then things don't change. If the difference is big, positive, then it goes up. And if it's big, negative, then it goes down. And as we get more and more and more episodes, this learning rate parameter is getting smaller and smaller and smaller. So we're making smaller and smaller changes. We're kind of honing in on the actual true value.
So this actually looks just like the update rule for perceptrons.
Yes. Yes. And in fact, that was, I believe, what Sutton was trying to do. He wanted to make temporal predictions, and he wanted to put it into the same kind of algebraic framework that people were familiar with from perceptron learning and from neural net learning.
Right. So if we did that way, then RT minus V sub t minus 1 is the error.
Very good. Yeah, that's a great way to look at it, that we're making our update based on moving a little bit in the direction of the error.
Right. Moving less and less and less as time goes on, which is just what you're supposed to do with the learning rate.
Exactly.
So let me ask a question along that line then. So along those lines then. So if alpha sub t was not 1 over t but something else, like, I don't know, 1 over the square root of t, or I don't know, something, some other way of doing the learning rate, you would get a slightly different answer. Would you expect at any given time, but would you expect to kind of converge to the same answer ultimately?
That is a really good question. In fact, that was the next question that I was going to ask.
Oh, wow. I feel better now.
So here it comes. So that was very astute of you. And in fact, there's a very general property that can be stated about learning algorithms of this type. So if we have a learning update rule, like the one that we have, which is that the value at time t is the value at time t minus 1 plus some learning rate times the difference between the new estimate and the previous estimate, or the new observed value and the previous estimate, then this VT will actually go to the true expectations, the actual average value of the R's, once t is big enough. Okay, so that's
Okay.
good. That means it's actually learning the right thing, but there are conditions that we have to put on the learning rate sequence. And the learning rate sequence has to have the property that if you sum up all the learning rates, it actually sums up to infinity. It's unbounded, it diverges.
As opposed to greater than infinity.
Oh, good point. Yes, that it's equal to infinity. Very good. It's actually greater than any finite number.
Mm-hmm.
Anyway, yeah, so it diverges. But the square of the learning rates, if you sum those up, it's less than infinity. And we're not going to get into the details about why these are the standard properties for making this kind of learning rule work. But to a first approximation, the learning rates have to be big enough so that you can move to what the true value is no matter where you start. But they can't be so big that they don't damp out the noise and actually do a proper job of averaging. So if you just accept that these are the two conditions that make sure that that's true, that gives us a way of choosing different kinds of learning rate sequences.
Okay, so what's some alphas that satisfy that and some alphas that don't? Alpha sub t's that satisfy that and some that don't.
That was a really good question. So let's turn it into a quiz. So here's 5 different examples of learning rate sequences that you might consider using in one of these kinds of learning algorithms. There's our friend 1 over t, which came out of the analysis that we did to get out the average. So we're hoping that one should really work. But then let's look above and below it. So 1 over t squared, 1 over t to the 2/3, 1 over square root of t. And actually, it's sometimes pretty popular to use learning rates that are just a constant, just a small number that just stays constant over time. And so what I'd like us to figure out is which of these 5 rules satisfy the two conditions. In other words, that the sum of the learning rates is infinite, but the sum of the squares is finite.
Okay, we can probably do that together.
Cool.
Okay, well, go.
All right, so to actually figure this out, we're going to need to check these two conditions. So we might actually find it useful to check each one of them individually. So here's the sum of the alphas, and here's the sum of the alphas squared.
Okay.
All right, so how are we going to start filling some of these in? Are there any of these cases that we actually know what the sums are going to be?
Yeah, 2 of them, I think.
Okay.
At least. So, well, let's go ahead and get the easiest one out of the way first. So I think that's I think 2 of them are equally easy. Let's do number 5.
Great.
So we know that that's going to be infinite. The sequence will be infinite because it's a constant.
Yep.
And we also know the square of which is also just another constant, and
Yep.
that's non-zero, so it's also going to be infinite.
All right, so what does that tell us about this learning rate?
It says if your learning rate doesn't get smaller over time, then you're never going to converge.
That's right. So this learning rate doesn't work as far as the theorem's concerned.
Right.
All right, you said there was another easy one.
All right, so number 2 I think is easy because you told me last time that one works.
Yeah, I guess that's a reasonable way to do it. Do you recognize the sum of these? Do you know what this is called if you sum up alpha t's of this sort of form?
Isn't it a geometric series or is it a harmonic? Which one is it?
Harmonic. Yeah, that's right. That's the harmonic sequence, and the sum of this up to t acts a lot like log of t. So as t goes to infinity, we do get infinity there.
Okay. And we also know that the square of it is less than infinity because you told me so last time.
Yeah, though that's, again, not the greatest reason. It turns out that any time that the power that we're raising the t to in the denominator is bigger than 1, it's going to converge. And so that gives us both of these boxes, right? Because it's the same thing.
Mm-hmm.
This problem in particular, this one, it converges. The value that it converges to is really interesting. I don't know if you know this, but if you sum up the infinite sequence of 1 over t squared, you get pi squared over 6.
Oh, right. Yes, that's obvious.
No, it's not obvious.
Well, explain it to me then.
I can't. It's bizarre. It's like, where's the pi? Where's the pie? I want some pie.
I ate it.
All right. So this problem was known as the Basel problem, and for hundreds of years people didn't really know how to solve it, and Euler worked on it and solved it, but he didn't solve it validly, and he eventually came back and solved it right. But it's kind of a remarkable thing that, pies come up when you're doing areas of circles and things like that. There's no circle here, so it's kind of interesting that you get a pi squared.
Well, r squared, right? Pi r squared.
Pi r squared.
Right, that's the area.
Sure, but the pi's not squared. It's weird.
I agree it's weird. I mean, I think I vaguely remember this from Calc 2 or something.
Cool. All right. Well, anyway, so that's just a sort of a fun thing that I find to be fun. But the point is that if we then square, let's look at the first row here. If we square t squared, we get t to the 4th, which is bigger than 1 over t, so that one's also going to converge.
Mm-hmm.
So what does that give us in terms of answers here?
No and yes.
Exactly, right. Because we need it to be infinity and then less than infinity. One of these boxes we've actually figured out, because this 1 over t to the 1/2, or the square root of t, if you square that, that's 1 over t. So this squared box has to be the same as this one. So that's infinity. And actually, that tells us the answer for this one even before we figure out the rest.
Yeah, I guess so. But I mean, you gave the answer away a long time ago
How so?
because you said that if the exponent was greater than 1, then it would converge. And if it was less than 1, then it would not converge. So I can just look at the numbers at the exponent for number 3 and number 4, and I already know the answer.
All right, so let's just fill them in then. Go ahead. What do you got?
Okay, well, let's see. If the exponent is greater than 1, then it will converge. Less than infinity, so that's true for neither 2/3 nor 1/2.
All right, so these are infinities.
Right. And you just have to square them and ask the same question.
Good. All right, so we squared this one, and that gets us 1 over t,
Mhm.
which also adds to infinity.
Right.
And you square this one, and you get 1 over t to the 4/3, which is bigger than 1.
Mm-hmm.
So that one should converge.
Right.
So interestingly, this one works, and this one doesn't.
Right.
So I think this leaves us in a position where we can actually state the TD1 update rule. So it looks a little hairy, but we're going to be able to go through it and see that it does something very sensible, or at least somewhat sensible. So this is the structure of the rule of TD1. So for each time we start a new episode, we're going to initialize this thing called the eligibility, E of S, for all the states to 0. So we just start them off as ineligible at the start of the episode, and we start off our estimate for the value function for this episode to be initialized to whatever it was at the end of the previous episode.
That makes sense.
So then each time we take a step within the episode, a step from some s little t minus 1 to some state s little t, getting reward rt, what we're going to do is first update the eligibility of the state that we just left, then go through all the states, compute this one quantity, which is the same for all states. This is the temporal difference. This is the difference between, or the sum of the reward plus the discounted value of the state that we just got to, minus the state that we just left. And we're going to use the values of the, that we had from the previous iteration, the previous episode. That's going to be our temporal difference. And we're going to apply that temporal difference to all states proportional to the eligibility of those states and, of course, the learning rate, because we don't want to move too much. And we're just going to update them by that. We're going to increase them by this temporal difference times the eligibility. Then we decrease or decay the eligibility for those states. And then we're back up to the next step.
Okay, it's got all the right letters, so I think I can imagine that this will do something. So the for all s part, does it have to be done in a specific order?
No, because the s's are all being done in parallel here. So the value at state s is going to be updated based on this quantity, which is the same for everybody. It doesn't depend on which s we're currently updating. And this quantity, which is specific to the s that we're looking at. So it's all kind of happening in parallel without any dependencies between them.
Yeah, okay, I see. So because there's an order to the states and the way we're going to visit them, you basically get to see that value kind of applied everywhere. Okay, I think I understand.
Okay, all right. So let's kind of step this through in a tiny little example, and then see the magic of it. See that it actually produces the same outcome that we would have gotten with the update rule that we had talked about previously.
Okay.
All right, so let's walk through the pseudocode with a very tiny little example in mind, just to see how the value updates work. So what we're doing here is we start off at the beginning of an episode. We say that the eligibility for all the states is 0. And the new value function is whatever the value function was at the end of the previous episode. So we just make a note of that. What we're going to do for this example is just keep track of the changes. So this ultimately it's all going to get added to whatever the previous value was. All right, so now we make a transition, and the first transition we make is from S1 to S2 with reward R1. What does that do to the eligibility?
Well, for S1, it sets the eligibility to 1.
Good. All right, then we're now going to loop through all the states, all of them, and we're going to apply this same little update to all of them. And the update has the form, whatever the current learning rate is, times the reward that we just experienced, the R1, plus gamma times whatever the previous iteration value was for the state that we landed in, minus the previous iteration's value of the state that we just left. All right, so this quantity is going to actually get added to all the states, but the amount that it's going to get added to all the states is proportional to the eligibility for that state. And since at the moment states S2 and S3 are ineligible, right? They have their eligibility set to 0. Really nothing's happening there. We're only making an update with respect to the state S1.
Oh, okay, I see. So then why are we bothering?
Well, it's not clear yet. For now, let's just make sure that it does the right thing. Then we'll talk about why it's a reasonable thing to have done.
Okay. I trust you, Michael, implicitly.
All right, so that's the changes that we've made so far to the new value function for S1, S2, and S3. All right, now we take the next step, which is from S2 to S3. Oh, wait, no, sorry. Before that, we have to decay the eligibilities for everybody. So the zeros decay to still 0, and the 1 decays down to gamma. All right, now we're done that update from the step that we just took. We take the next step, S2 to S3, reward R2. So what does it tell us to do? Well, the first thing is we have to update the eligibility of the state that we just left. So that bumps S2's eligibility up to 1. Then we go through everybody and we add this quantity again. So what's the new quantity? It's R2 plus gamma times the value of the state that we just left minus the previous value of the state that the state we just got to and the state we just left. All right, so this is this update that is now independent of which state we're actually changing. We're going to apply that everywhere, but we're going to apply it proportionally to the eligibility. So the eligibilities are at the moment gamma 1 and 0. So gamma 1 and 0. So we just have to add this into the other things.
What does that look like?
So through the magic of cut and paste, we can actually add that same complex quantity to both these updates here. And in particular, we're multiplying by the eligibility. So for the first value, we have this extra gamma in here. For the second one, nothing. And for the third one, it gets multiplied by 0, so I didn't even bother to write it. So this is starting to look a little bit hairy, but that's okay because we're going to do some simplification.
Okay.
So here's the interesting thing to observe, that previously we added in this value of S2 according to the previous value function times gamma, and now we're subtracting away the value of S2 from the previous iteration, and we're multiplying that by this gamma and this alpha. So they actually match exactly. This thing and this thing cancel.
That's beautiful.
So now I can rearrange the remaining terms and make it look a little bit simpler. All right, and this is the simplified form that we get. It compactifies really nicely, actually. And so we have something that's of a similar form that we had before. But the point is that mainly what just happened is we regrouped terms, and the S2 related stuff in this term, in this update here, canceled. So the last thing we do after we've done all those value updates is we update the eligibilities, and we're ready for the next step. The next step takes us from S3 to SF, and we get reward R3 when that happens. The first thing that happens is we update the eligibility for that state. Then we compute this quantity that we're going to add to all the state updates. This gives us R3 plus gamma times the previous value of the state that we just ended up in minus the state that we came from. And this update is going to get applied to all the states proportional to their eligibility. So we can do that same thing again, just add this quantity into all these things and simplify. Does that sound okay?
It does sound okay, and I think I finally see where this is going. So if you look at the pseudocode, right, you say for all S, and you update the value of the state. Mm-hmm. If you look at the stuff that's multiplied by alpha sub t, mm-hmm. all that is basically is your error, right?
Mm-hmm. It's temporal difference error, right? That's why this is TD learning.
Right. So it's what you thought it was. The difference between what you thought it was and what it turned out to be when you actually saw the reward, mm-hmm. if you assume that your future guesses about the values are right.
Exactly.
So because of that cute little compactify telescoping thing that you just did, I think without actually writing everything out, I can guess what the next values are going to look like. So, and tell me if I'm right. So the delta for VT of S1 mm-hmm. is basically going to have seen one more thing. So it'll end up being R1 mm-hmm. plus gamma R2 mm-hmm. plus gamma squared R3.
And where does that come from?
That comes from the term that you just added over there.
Well, the R3 right? And the eligibility for state S1.
Right, which you've managed to make the gamma squared. So the eligibility isn't just whether you've seen a state before. It's actually keeping track of how long ago you saw that state.
Good.
Right. And so if there was another state after SF and we kept going, we'd see that would become gamma cubed, mm-hmm. and S2 would become gamma squared, and S3 would become gamma, and so on and so forth. That's quite clever.
Mm-hmm.
Okay, so you would see R1 plus gamma R2 plus gamma squared R3
Mm-hmm.
plus gamma cubed of VT minus 1 of S4.
Well, there's no S4, so the final state.
I'm sorry, SF, thank you. Thank you very much, of SF, minus VT minus 1 of S1, so that stays. And all that is the error. It's what your guess was of the value and what you actually ended up seeing, which was all the rewards that you saw plus whatever future value there's going to be.
Good. All right. Well, so that we may have done a little bit too much jumping. So can I fill that in with the way that you just described it?
Okay.
So some frustrating amount of algebra and rewriting later, it seems to have fallen into this pattern. And this is what you're talking about, right, Charles?
Yeah, this is exactly what I was thinking.
So we have these sort of temporal differency things. So we can now state a claim, which just follows very clearly from the example. And that is that this update, this TD1 update that we just talked about, actually does the same thing as the outcome-based update, which is to say we wait to see what all the rewards, the discounted rewards are on the entire trajectory, and then we just update our prediction for the state that they started from with those rewards. Keep in mind that these things are zero, right? The SF, VT minus 1 of SF is 0. So this kind of goes away, and this kind of goes away, and this kind of goes away. And we're really just talking about the discounted sum of rewards minus the old prediction. The discounted sum of rewards minus the old prediction. The discounted sum of rewards minus the old prediction. So at least in the case where there's no repeated state, so we visit a state more than once along a trajectory, everything beautifully cancels, and what you get is exactly the same update. The TD1 update is exactly the same update as just waiting for the outcomes and updating based on that.
That's actually really impressive. So what happens if there are repeated states? So if there were repeated states, then, oh, I see. So, okay, so let's imagine that we did outcome-based updates sort of, but without, and we saw repeated states, and all you're really doing is ignoring anything. Oh, I see. Okay. How about this, Michael? Tell me if what I'm saying makes sense. So
Sure.
if we were doing outcome-based updates, then basically you're just looking at all the rewards that you see, the values that you kind of expected along the way, and it's exactly what you have written down before. But if we had a repeated state, then you're basically ignoring anything you learned along the way. So
during the
that's not
episode,
helpful.
right.
During the episode. So outcome-based updates say learn nothing during the episode. So if your sequence up there, instead of being S1, S2, S3, SF, had been S1, S2, S3, S1, SF,
Yep.
then what would have happened is I would have seen the rewards that I saw, R1, R2, R3, and then some other reward that I would see. Let's call it R1 prime or something. I don't know. I would be pretending as if I didn't already know something about state 1 because I also saw it go from state 1 to state 2 and saw a particular reward, R1.
Yes.
I'd be ignoring that. So what this TD1 update lets you do is when you see S1 again and you sort of back up its value, you've actually captured the fact that last time you were in S1, you actually went to S2 and saw reward R1.
Right, exactly. So it's like the outcome-based updates now with extra learning or inside the episode learning.
I like it. Beautiful. So is that better?
Let's say yes.
Excellent. That makes me feel good about myself.
All right, Charles. So now that I've talked through how we can compute these outcome-based estimates or these TD1 estimates, I'm going to try to tell you that it's not exactly what we want. So I'm going to try to explain why TD1 kind of is wrong sometimes.
Okay.
And to do this, we're going to go back to the example that we looked at before, where we've got this Markov chain with rewards. And we're observing some trajectories through it, like S1, S3, S4, S final. And so we observe a bunch of those. And then in the last one, we observe starting from S2, S2, S3, S5, SF. Okay? And now what we want to figure out is what does TD1, or an outcome-based estimate, give us as an approximation for the value of S2 given this set of data. And then we'll compare it to what we get with the maximum likelihood estimate.
Okay. Wait, you want me to do this?
Yeah.
Oh, okay. So it really is a quiz.
Yeah, that's what this word is. Yeah.
All right, fine. I think I have some questions, but in fact, let me ask some of them now. So,
Yeah, I think we should make sure that it's clear enough so you can work on it.
okay, so you want me to tell you what the value of S2 is, or what I would estimate the value of S2 to be using
Right.
sort of the TD1 outcome-based estimate?
Which and there it should be the average of the the reward sequences that we've seen upon encountering S2.
Okay, that makes sense. But that has to start from somewhere, right? The equations require you start from somewhere.
We could just average it across all the encounters that we've had of that thing. So since we're averaging, the first time we see it, that is the estimate. The second time we see it, that's half of it. And
Okay, that's fair. Okay, I can deal with that. And by maximum likelihood estimate, you just mean, the value that best fits the model, which in this case is the MDP itself?
yeah, so given the data that we've seen so far, you can make an estimate of how likely it is to go from S3 to S4, S3 to S5, S1 to S3, S2 to S3. So you can use the data that you've seen to estimate the probabilities in this model, which aren't going to be exactly what they show here because this is the true model, but we can estimate it based on the data, and then we can say, okay, given that estimate, what is the value of S2?
Okay, that seems reasonable. Okay, I can do that.
All right, but you probably should also ask what the discount factor is.
Oh, yeah, what's the discount factor?
Good question. Just for simplicity, we'll go with gamma equals 1 again.
Okay, go. Okay, so let's go through this.
Good.
So let's look at the outcome-based estimate.
Good.
I think you kind of gave me everything I need here. So
yeah, it's possible I spelled it out too detailed.
you could never spell it out in too detailed a way, Michael. So if I look at it, we encounter S2 exactly once.
Exactly once.
And so the average of 1 is pretty easy. It's that thing.
Okay, and what is the estimate for that one?
Well, 2 plus 0 plus 10,
Yeah,
which is 12, because gamma's 1.
because gamma's 1. So good. So this is saying because we've only ever encountered S2 once, and the one time that we saw it, we ended up with a reward of 12 getting to the final state. That's going to be our estimate. And that's what TD1 would actually do, modulo the learning rate and how you initialize the values and so forth. But that's sort of what it's trying to be like given this data.
Right.
All right, so now does that match with the maximum likelihood estimate, the estimate that we'd get if you used the data to build a model and then solved it?
So for the maximum likelihood estimate, all I really need to do is to compute, let's see, the probability from going from S3 to S4 and the probability of going from S3 to S5, because everything else is deterministic. And in all 5 of those transitions, I get to see every state and every reward. So I have everything that I need. So let's just go ahead and estimate the probability. So looking it through, I go from S3 to S4 3 times.
2, 3 out of
Out of
5 times that
five.
we're in S3.
Right.
Good.
So that would be 0.6.
3/5 is 0.6. Yes, got it.
All right. And by process of subtracting, that means that going from S3 to S5 happens 0.4 of the time.
Yeah.
All right.
And we could compute that directly too by just counting. We get twice out of 5 times.
Right. So those aren't right. It should be 0.1, not 0.4, and it should be 0.9, not 0.6. But hey, it's the data that we've got.
Yeah, and yeah, you're right. I mean, it's much more even, but it is still S4 is more common than S5.
Right. Okay, good. So with that, I can just, propagate values backwards through the MDP, just like we did on the final exam for 7641. Okay, so
Good.
So let's see. The value of SF is 0. The value of S4 is 1.
Mm-hmm. One more.
1 plus 0. And the value of S5 is 10.
Good.
Plus 0.
All right. So, and that's all actually correct.
Yeah, that is actually correct. Thank you, determinism. Okay. So S3 then, 6/10 of the time we'll get a value of 1, and 4/10 of the time we'll get a value of 10. So that would be 0.6 plus 4.
4.6?
That is indeed 4.6.
Cool.
All right, so who cares what S1 is, but I guess we can go ahead and compute it. It would be 5.6.
Good.
Because it's plus 1, 4.6.
But the actual question was about S2. Dun, dun, dun.
And so it is 6.6.
6.6.
Proof by addition,
All right.
and it works out pretty well. Okay, so 6.6 is very different from 12.
Sure.
I'm not sure if either one of them is right. So let's see. If I recall, when we went over this MDP before, using the actual transition probabilities, zero point
Yep.
0.9 and zero point 0.1, we figured out that the value of S3 was 1.9.
Yep.
Yeah, and we can check that. Like that would be 0.9 times 1 plus 0.1 times 10. So yeah, that'd be 1.9, which means the value of S2 would be 3.9.
All right. So the actual value is 3.9. The maximum likelihood estimate is 6.6, which is more, but the outcome-based estimate is 12, which is a lot more.
Right. So everybody's wrong except for 3.9, but maximum likelihood estimate is less wrong.
Right. And so why in this case? Like what's the difference between these cases? First of all, why are these so far off? And second of all, why is the outcome-based one even further off than the maximum likelihood?
Well, I think it's pretty simple, right? When we computed the outcome-based one, we basically only used one of the 5 trajectories to propagate information back. But when we did the maximum likelihood estimate, we used information from all 5 of the trajectories, even though we only encountered S2 once.
Mm-hmm.
And so that's just more information and it's more accurate. And you would imagine that if I triple the amount of data, the 6.6 would very quickly get closer to 3.9, and the 12 might not move at all if I never see S2 again.
Mm. Good. So this maximum likelihood estimate is actually using more of the data. I think that's accurate. The reason it's higher than it should be is because we got, I don't know, lucky, I guess, and had a bunch more transitions to the high reward state S5 than we would expect on average. And we got really unlucky, or really lucky, depending on how you think about it. From this one trajectory we did from S2, we got the unlikely outcome, which is high reward, and so we ended up with an estimate that is way higher than it really should be.
Yeah, but look, if let's imagine that we had gotten lucky the other way. There's only one other possibility, right? S2 to S3 to S4 to SF. And if that had happened, then we would have seen a value of 1 instead of a value of 10, and we would have had 3.
That's right. And on average, it's going to turn out to be the right answer, this 3.9. But this estimate is based on the limited data that we've got.
Right. Okay, fair enough.
All right. So, but the punchline here is that this TD1 idea, it's not using all the data. It's using just individual runs. And so when a rare thing happens on a run, you could end up with an estimate that's quite far off. And it could maybe stay that way for a long time. Whereas the maximum likelihood estimates seem to push you in the direction of using the data that you've got to do the best you can. And so what this is pointing out is that maybe we don't want to just do TD1. There's some nice things about TD1, but maybe we can shore up some of these other issues and come up with something even better.
What, without actually building an entire model?
Yes.
Okay, well, I look forward to that.
All right, so here is a rule we're going to call the TD0 rule, which gives it a different name from TD1, but eventually we're going to connect the 0 and the 1 together. And the rule looks like this, not so unfamiliar looking, that the way we're going to compute our value estimate for the state that we just left when we make a transition at epoch t, for trajectory t, big T, is what the previous value was, plus we're going to move a little bit in the direction with our learning rate toward what? Toward the reward that we observed plus the discounted estimated value of the state that we ended up in minus the estimated value of the state that we just left. So does this look familiar?
It's got V's and R's and alphas in it.
Well, sure. All right, but maybe we can be a little more precise about this. So what would we expect this outcome to look like on average, right? So the thing that's random here, at least the way we've been talking about it, is if we were in some state st minus 1 and we make a transition, we don't know what state we're going to end up in, but there's some probabilities of those. So basically this update is being done more often in the states that we end up in more often, the more common STs, and less often in the STs that are less common or less likely. And so really, if we take the expectation of this, what is it going to look like? If we repeat this update over and over again, what we're really doing is sampling different possible ST values, right? So really, we're taking an expectation over what we get as the next state of the reward plus the discounted estimated value of that next state.
That seems right. That's kind of what we want.
Yeah, so this is exactly what the maximum likelihood estimate is supposed to be, as long as these probabilities for what the next state is going to be match what the data has shown so far as the transition to ST.
Is that what that blue stuff above the equations is about?
Yeah, so here's the idea is that if we repeat this update rule on the finite data that we've got over and over and over again, then we're actually taking an average with respect to how often we've seen each of those transitions. So it really is computing the maximum likelihood estimate. So this does the right thing.
Oh, okay, over so that finite data thing is important because if we had infinite data, then everything would work.
So right, in the infinite data case, this is also true, but also TD1 does the right thing in infinite data.
Kind of everything does the right thing in infinite data.
Yeah, everything's going to all average out and it'll do the right thing. But here we've got a finite set of data so far, and the issue is that if we run our update rule over that data over and over and over again, then we're going to get the effect of having a maximum likelihood model. And that's not true of the outcome-based model because in the data that we just saw, where we only saw one transition from S2 to anything else, we can run over that over and over and over again, but the estimate's not going to change. It's always going to be exactly that.
Okay, that makes sense. Okay, sure. How about that?
We can contrast this with the outcome-based idea where we're not doing this sort of bootstrapping. We're not using the estimate that we've gotten at some other state. We actually use literally the reward sequence that we saw. And so as a result of that, if we've only seen a reward sequence once, like in the case of S2, repeating that update over and over again doesn't change anything.
Right. Sure. Because the expectation is the expectation.
Right. Whereas in here, we're actually using the intermediate estimates that we've computed and refined on all the intermediate nodes, on all the states that we've encountered along the way, to improve our estimate of the value of every other state, right? So this kind of is more self-consistent, right? It's actually kind of connecting the values of states to the other values of the states, which is what you'd want. And this is more just, literally using the experience that it saw and ignoring the fact that there's these intermediate states.
Okay, well, when you put it that way, it makes it sound like you should always use TD0 and never use TD1.
Yes, but that's oversimplifying.
Okay. Can you undersimplify it?
We'll get to that.
Oh, okay, good. I look forward to it.
All right, so now we've talked about two different algorithms, TD0 and TD1. And what we'd like to do next is show that, in fact, there is a larger algorithm that actually includes both of those as special cases. And so we're going to write that as TD lambda, and it's going to have the property that when lambda is set to 0, we get TD0, and when lambda is set to 1, we get TD1, but we also get update rules for all sorts of in-between values of lambda.
Oh, no, that sounds kind of like a witchcraft to me.
No, it's just algorithm design. It's all good.
All right, well, I'll believe it when I see it.
In particular, what's going to let us do that is the fact that both TD0 and TD1, the way that we were writing them, have updates that are based on differences between temporally successive predictions, temporal differences. That's the TD part. And so we can actually unite them into one, and I don't need to say that again because I've already said it.
All right.
So I copied the algorithm back down here. And do you know which algorithm this is? And the hope is that it's a little bit challenging because, in fact, if it's TD0 or TD1, they actually look an awful lot the same. They have a lot of stuff in common. The update rule itself looks almost identical, but they are different. So which one is this?
Well, I'm trying to remember, and let's see. There's a 0 in one line and a 1 in another line, so that's not going to help me. I was hoping I could count the number of ones and zeros.
Actually, there's a bunch of ones, right? There's a ST minus 1, and there's another 1, and here's another 1. And here's another one and another one.
Yeah, but most of those are minus ones, not plus ones. And you didn't ask me if it was TD minus 1.
So maybe this is TD negative 1.
Oh, that probably suggests that the way I was going about this was wrong. I think it's TD1.
All right. So, and do you have any particular reason for that?
Because I recall TD1 had a bunch of E's in it.
Yes, it is easy to tell the difference. So E here, the eligibility, is something that doesn't show up in the TD0 rule the way that we wrote it, but it does show up in TD1. This sort of idea that what we're going to do is we're going to update the values for all states, all S, and the amount that we do this same update varies depending on the current eligibility of that state in question.
Okay, that seems reasonable. I feel better now.
All right, and so to highlight the similarities and differences between TD1 and TD0, I took the TD1 algorithm that we just had and shrunk it and moved it over to the left, and then made another copy of it, put it on the right, and made the minimum changes necessary to turn TD1, what was TD1, into TD0. And so mainly all that involved was anytime the eligibility was mentioned, I kind of got rid of it. So I got got rid of it from there. I got rid of it from there. And I don't multiply it here against the temporal update, and I don't have to update it here. And the only other difference, other than just getting rid of all references to the eligibility trace, is whereas in TD1 we do this update over all states, in TD0 we just update the state that we left most recently. So I changed that loop instead of making it a loop, it just says for all s equal to st minus 1. In other words, we're just going to do this update for s equal to st minus 1. All right, so now we're ready to describe the TD lambda rule. What I've done now is I got rid of those words, and I took the TD1 rule and copied it up here. So this is currently TD1. And what we now need to do to it is make changes to it, small as we can, so that it turns it into TD0 when lambda is equal to 0. So we need to introduce a lambda. So here's what I'm going to do, just to kind of cut to the chase. I'm going to take this gamma decay of the eligibility, and I'm going to change it to a lambda gamma decay of the eligibility trace. All right. So all I've done here is it's the same. It's exactly TD lambda, except I just threw in an extra lambda here as a multiplier in the update of the eligibility rule, and boom, we're done.
Okay. So wait. Okay. Right. So I was raised to never put two Greek letters next to one another. But let's see what this does. Do I buy this? Okay. Let's see. So if lambda is 1, then well, nothing's changed. That's exactly the algorithm it was before.
Right, great, because if lambda is equal to 1 and we're just multiplying this lambda in there, then nothing's changed. So boom, it really is, and it was TD1 and it is TD1.
Right. So let's see, what happens if lambda is 0? Well, for the thing we just looked at, that means it's 0, so you just set ES, the eligibility trace equal to 0. So
right.
But you started out with it being equal to 0 too. So let's go back to the top. So let's see, for all S, E of S is 0, which is where we started out, the start of the episode. That's nice. Then we update E of S sub t minus 1 to be E sub S of t plus 1. So now E sub S of t is equal to 1.
Right, good. Okay, so the eligibility of the state that we just left gets bumped up to 1. That's right.
And everything else is 0.
Now we loop over all states.
Right. And we update V sub t of S to be this thing times, well, it'll be 0 for everything except for S of t minus 1.
Good.
And then we will take the eligibility for that state and set it equal to 0.
Right. So in particular on this update, the eligibility is 0 for all the S is not equal to st minus 1. So nothing gets changed there. And for the one where it is equal to st minus 1, this eligibility is 1. So we just do it, we just update based on that, which is exactly what we have for the TD0 rule. And then, right, as you say, then we zero out the eligibility and start it all again. So it's almost like it briefly remembers where it needs to update, and then it loses that memory right away. It goes right back into forgetful mode.
Although that won't matter anyway because you're doing it for every S once. And then you'll pop back up and do the episode again, and you start all over again. It's like an invariant. And so...
Oh, but that's only at the end of the episode. So we really only pop back to, right, when we're doing these updates, this is after each little t transition. So this part we're actually going to execute over and over and over again until the end of the episode. So we don't zero out the eligibility until the end of the episode. But in fact, using lambda equal to 0 here has the same effect as it. So we don't really need to do that.
Exactly. Okay. So then the right thing happens.
Yeah. So when lambda is equal to 0, boom, we get TD0. When lambda is equal to 1, boom, we get TD1. And so I guess what makes this interesting is not just that we can cleverly shoehorn two algorithms into one, but that it allows us to actually use values of lambda that are in between, which gives us kind of elements of both of these. It has TD0-ish things to it and TD1-ish things to it. And what we're going to look at next is how to think about this rule, this generalized TD lambda rule, so that it kind of makes some sense, to kind of ground it in quantities that we can understand.
Okay, well, I look forward to that.
So it turns out if we want to understand TD lambda, a really useful way of studying it is by studying not TD lambda. So in particular, we're going to look at k-step estimators for a moment, and then we're going to relate that back to TD lambda. So here's what a k-step estimator is. So let's say we're trying to estimate the value of a state, st, so it's a state that we just are leaving, as a function of what happens next. So let's look at this first estimator here. It says that we're going to estimate the value of a state that we're leaving by moving it a little bit in the direction of the immediate reward plus the discounted estimated value of the state that we landed in. And we're going to just move a little bit in that direction. So do you recognize this? Have you seen this before?
I believe I have seen this before.
What did we call it?
I don't remember anymore.
Oh, well, that's unfortunate. So
But
it's
I've seen it before. It's just like a one-step look-ahead sort of thing.
yeah, exactly, which is what we were calling TD0.
Oh, right. Yes. Yes, that makes sense.
And in fact, you're exactly right that the way to think about that is as a one-step estimator, right? So it's a one-step estimator in that we use the immediate reward that we got plus the value of the state that we land in. But let's contrast that with a two-step estimator. We'll call it E2, estimator 2, where what we do is to estimate the value of a state that we're leaving. We're going to move a little bit in the direction of the immediate reward that we received plus the discounted reward that we received next plus the double discounted value of the state that we landed in 2 steps from now. So now instead of where before we did an estimate by taking one reward and we estimate the rest of the sequence using our current estimates, here we're taking 2 rewards and using that as our immediate estimate plus our estimate of the future taken as the state that we reach 2 steps from now. So does that make sense kind of as an extension of that idea?
No, that makes sense. So if E1 is a one-step look ahead, then E2 is a two-step look ahead.
Yeah. Yeah, exactly. So we use 2 steps, 2 real steps, followed by this kind of look-ahead thing. And we could do that for 3, right here. And we could do that for K, where we're estimating the value of a state by K rewards, summed up here, plus, and then we estimate the value of the future by looking at the state we end up in K steps from now and discounting that by K steps. And in fact, if we continue doing this arbitrarily, we eventually get to E infinity, where let's see what would happen in that case. So we get the sum of rewards, and it keeps going and it keeps going. And eventually, at infinity, we look at the state that we end up at infinity, which of course isn't a real thing. But then it's okay because we discount it by gamma to the infinity, which is 0. So this piece of the term actually drops out, and we just end up with this infinite sum of rewards. Now, this last estimator should look familiar to you too, Charles.
Yeah, that looks like TD1.
Good. So now we've got TD0 on the one side as a one-step estimator and TD1 on the other side as an infinity step estimator. And we've got these other things in between that we don't really have or possibly even need a name for.
Well, that makes a lot more sense with the title K-step estimator. So I was worried this was going to turn in some kind of commentary about dubstep.
Oh, yes, break it down. So that's not going to happen in this case.
It's probably for the best.
So what I need to do next is actually relate these quantities to TD lambda, which we're going to show is a weighted combination of all these estimators.
All infinity of them?
All infinity of them.
Oh, that's pretty impressive.
So here's how we relate the K-step estimators that we just talked about with TD lambda. So the idea is this. We're actually going to be using a weighted combination of all of the estimators on for any one of these TD lambda algorithms. And the weights are going to look like this. 1 minus lambda for the one-step estimator, lambda times 1 minus lambda for the two-step estimator, lambda squared times 1 minus lambda for the three-step estimator, lambda to the k minus 1 times 1 minus lambda for the k-step estimator, and then all the way down to essentially lambda to the infinity, but of course that one literally doesn't get any weight.
Wait, what's...
Except, well, actually, let's leave it at that for now, and then we'll explain why that's an okay thing to say in a second.
Okay. So far everything you said makes sense, except you haven't told me what you're weighting exactly.
Oh, so what we're going to do is when we move the value, when we change the value of a state, we're going to change it by all the different estimators. All the different estimators are going to give us their own preference as to what we should be moving the value toward. And we're just going to take a convex combination, a weighted combination of all of them each time that we do an update for the value of a state.
Oh, I see.
Now, we don't literally get to list all of these and update based on them, but equivalently, this is what we're doing. And so there's a couple things that we should probably check. One is we should probably make sure that these weights sum up to 1.
Mm-hmm.
So how do we do that? So let's see.
You read a summation?
Good idea. So the summation is all the different estimators from 1 to infinity of the weight applied to that estimator, which this formula works for all the different values of k. For k equals 1, it's lambda to the 0, which is 1 times 1 minus lambda. So we can now factor out the 1 minus lambda. As long as lambda is less than 1, we can use this as the geometric series, and we get 1 over 1 minus lambda, and that's going to cancel with this 1 minus lambda, and so the weights sum up to 1. If lambda equals 1, though, what happens then? These are all zeros, and then this infinity one is 1 to the infinity, which is just 1. So when lambda is 1, we put all our weight on this last estimator. And what happens when lambda is 0? So if lambda is 0 in this case, we get a weight of 1 on this first estimator and 0 on all the rest, which I'll write down this way. And when lambda is 1, we get 0 for all these except for the last one, which, let's say, at least in the limit, would be 1. So this is actually, as we said, this is giving us TD0, and this is giving us TD1. So if we just use lambda in place of 1 and 0, which works, then we get TD lambda. But the important thing is that for in between values of lambda, like a half or 0.3 or something like that, we actually get weights on all of these to some degree. And it's combining all those different estimators together.
And that seems okay. Any good characterization of what that weight looks like? So if lambda were equal to 1/2, is that exactly halfway between TD0 and TD1?
Well, when lambda is a half, what do our weights look like? We get a weight of a half on this one. We get a weight of a half times a half, or a quarter, on this one. We get a weight of a half times a half times a half, or an eighth, on this one. So we get this sequence of decreasing weights, exponentially decreasing weights. Is that halfway between these two things? I don't know. I suppose you could define it to be, but it is just what it is. It's a combination of a whole bunch of estimators together.
Right, that eventually gets to 0.
Sure. But again, we're combining the outputs of all these estimators. We're using whatever update they're suggesting, and moving a little bit in the direction of the first one, and a little less in the direction of the second one, and a little bit less in the direction of the third one, and so on. So yeah, in the limit, we're not actually doing the E infinity estimator at all, but that's okay because we're doing all these other estimators that kind of lead up to it. So I don't know. Does that help you understand TD lambda better? This is the way I think about it. Is to say, well, it's a little bit hard to interpret, but what we're really doing is doing a weighted combination of a bunch of step estimators instead of this sort of strange continuous parameter.
Well, I mean, I guess so. I mean, when I think about it the way you put it, I guess what you're saying is, look, you could do one step look ahead, or you could do two-step look ahead, or you could go all the way into the end of your episode, which may last forever, and you could pick any one of those, or you could say each one of those, gives me some information, and I should just figure out some way to combine them. And I can pick various ways of combining them, and I don't particularly know how to turn the way I combine them into a simple English sentence, but I am finding ways to combine various ones of them, and I should pick some value of lambda that seems to work for the problem that I care about.
Yeah.
So there you go.
All right, so now given that we don't actually have a crisp characterization of what something like lambda equals a half really gives us in words, why do we care about these intermediate values? So I'm going to make a transition and talk about next what happens empirically when you use TD lambda.
Okay.
All right, so let's see if we can think through or maybe guess what's going to happen if TD lambda is run as an update algorithm on some finite amount of data. So we give the system some finite amount of data, and then we run TD lambda with different possible values of lambda, and then we ask, all right, the V that you've learned, how far is that from what the V should have been if we had infinite data? All right, so let's let's sort of see if we can figure out or maybe even guess what this might look like. So let's say if we use lambda equals 0, so we do TD 0. So after some finite amount of data, there's going to be some amount of error. Let's just, I don't know, call it that.
Okay.
Now, it turns out empirically, if you play with this, it's pretty typical for TD1 to give you worse error given finite data. And now the important thing is what happens in between. So it could be like a straight line if it was literally interpolating. It could be kind of bowed up, but it's actually typically bowed down. So it's not so atypical to see a curve kind of like this, that gets better. The amount of error goes down as lambda gets to some intermediate value. Let's call it, I don't know, 0.7. It depends, of course, on the particular problem. And then kind of start to shoot up again and eventually hit the error for TD1 as lambda approaches 1. And so this is kind of the justification for why we want to consider TD lambda, that it's actually combining these two different sources of information, what happens at the end of an episode and what happens at each step, in a way that actually takes advantage of both. It gets you the benefits of both. We're rapidly propagating information, and we're not getting a biased estimate because of the way that we're using one-step information. So it It has some attractiveness to it.
Huh. Did you pick point 0.7 on purpose? I remember reading a paper once that suggested that basically everyone uses lambda equals a point 0.7.
I typically see, zero point 0.3 to zero point 0.7 as values where things tend to work out, where this bottom tends to fall somewhere between zero point 0.3 and zero point 0.7. Personally, I I always use 0 because it works better with control. I have had better performance and better understanding of what happens in the 0 case. But it is true that if you actually run it with a finite amount of data, it tends to bottom out somewhere between 3 and zero point 0.3 and zero point 0.7.
Okay, that's worth knowing.
So that's actually all I wanted to tell you about TD lambda. I wanted to give you a sense of how the equations are defined and how they're derived, and empirically why this is something that we actually care about. So maybe we should sum up.
Oh, I'm a big fan of sum. Is this going to be an infinite sum? Thank you. I've been here all week.
Okay, Charles, so we've been talking about temporal difference learning, and in particular, various flavors of the TD lambda algorithm. Can you remember some of the important things that we touched on?
Well, I think you just said the big one, that all this discussion has really been about temporal difference learning.
And in a nutshell, what's a temporal difference?
Well, it's the difference between things you see on different subsequent time steps.
Yeah, what kind of things in different time steps?
Reward.
So sort of the difference in value estimates as we go from one step to another, right?
That's exactly right. Because value is just a nice summary statistic for long-term reward.
Good. All right.
But actually, I think it was important that you started off talking about this is the thing that we wanted to do, but first you put it in context by talking about different ways that we could solve the reinforcement learning problem. And as I recall, there were sort of three ways to think about it: model-based learning, value-based learning, and then let's say policy-based learning.
That's right. And TD methods kind of fall where?
And the value-based.
All right. And then we dove into the update rules themselves. So what do we talk about there?
Well, we actually derived.
Derived?
That seems either one of those things. It's just semantics. This kind of incremental way of building up estimates of the values. And I think you called it outcome-based. And I suppose, and all that really means, of course, is that, you actually look at the outcomes of what you experience from different trajectories and episodes through the space, and you use that to build up your sort of estimate of what the values of various states are.
Yeah, and in particular, the idea of an outcome-based says, well, you can kind of treat reinforcement learning as a kind of supervised learning. Just wait for time to stop and see what happened and use that as a training example. But we can't really wait for time to end because it's kind of too late to use any of the information there. So what we want are incremental methods that can actually do updates along the way that would be equivalent to waiting to the end, but actually gives us results sooner.
Right, and there was a technical point that you made that I guess is something that we learned about, which we had talked about in the old machine learning course, but we didn't go into any detail about, which is this sort of incremental update. By making it look like a supervised learning rule, just look like the normal perceptron update rule, and it had a learning rate. And in order for us to be sure that we were going to learn something we wanted to learn, that learning rate had to have certain properties.
Right, that's exactly right. And in a nutshell, what were these properties that the learning rate had to have?
Well, let's see, that the sum over all the learning rate values, so let's call that alpha t for time, needed to be infinite. And that the sum of the learning rates squared needed to be finite.
Yeah, and so intuitively, we wanted learning rate sequences that would allow us to move the value to wherever it needed to go to converge, but would dampen over time, decay, so that the estimates wouldn't keep bumping around as a function of the noise.
Right, I think that's great. Well, anyway, I think that pretty much brought us to the end. I mean, we took a lot of slides to get there, but it turned out the algorithm that we derived looked a lot like something we called TD1. We gave it a nice little name. And TD1 was very nice, except it was inefficient in the way that it used data.
Yeah, I don't know that everybody would agree exactly with that way of characterizing it, but it is true that it had this sort of weird property that it was there was a lot of variability in it. There was a very high variance because if we had one run, we had a value that we were estimating from one place, and the estimate was based on a very noisy example, then we were going to have a very noisy estimate. It wasn't going to be able to use the rest of the examples that it's seen to kind of smooth this out.
Right. It just sort of didn't get it didn't use information along the way. It used information sort of at the end of every episode. And that's what made it sort of data inefficient. And I guess in the end, that gives you high variance. But we came to the rescue, and when I say we, I mean you, came to the rescue with TD0, which has the nice property that it gives you the maximum likelihood estimate.
I prefer to think of it as the Michael Littman estimate.
Yeah, I know you do. I've seen how you snuck that in. And then it got us to the very end, which is good because you're running out of space on the slide. We generalized TD1 and TD0 into something we call TD lambda.
Right. That has the property that when lambda is 0, we get TD0. When lambda is 1, we get TD1. And what about the intermediate values?
Well, then that just gives you a dubstep.
Wait, what?
It gives you dubstep. You get the dubstep look ahead.
I see. That's right. Multiple steps of updates. I see what you mean by dubstep. Like you double the number of steps.
Oh, yeah, I like that. That sounds like I meant to do that. Yeah, let's go with that. And there you go. I think that's just about everything. Oh, one more thing is that you talked a little bit about different values of lambda and why you might choose one value over the other. And it turns out that values of lambda between, 0.3 and 0.7 empirically seem to work pretty well.
Yeah, because it somehow is making a nice trade-off between giving estimating the right kind of quantity and estimating it using, the values that you get from looking ahead.
Right. And that's kind of, first off, that's neat because otherwise you wouldn't need to have TD lambda. But it's in some ways a little surprising.
Why is that?
Well, because it just kind of works out the way that you would want it to work out. You went through all this trouble to kind of generalize between things. You have this kind of highly nonlinear way of combining all the different k-step look-aheads. And it turns out that combining them so it's not quite 0, it's not quite 1, is better than either 0 or 1. And often that's not how it works, right? Often it's like a line from 0 to 1 is better. It's like a line, or it gets really better than it sort of flattens out towards the end, like you said. But in this case, it just gets better and better and better, and then it starts to get worse when you go from one end to the other.
Yeah, that's right. So often when you combine two good things, you get the worst of both. And in this case, it does somehow manage to get the best of both.
Yeah, that's pretty cool.
All right, so what I would like to dive into next is a deeper understanding of how we could show that these kinds of methods actually converge and they actually produce optimal estimates and optimal behavior in the limit. And so we're going to take a step back and look at the Bellman equation again to do that.
Oh, I like it. I love the Bellman equation.
All right, see you then.
All right, see you. Bye.